going to talk about linearization and differentials. So let's talk about linearization first. So if f is differentiable at x equals a, then the approximating function L of x equals f of a plus f prime of a times quantity x minus a. Now, is the linearization of f at a, the approximation f of x is approximately equal to L of x of f by L is the standard linear approximation of f at a. Okay, the point x equals a is the center of the approximation. Okay, that's a lot to talk about. Really what that is saying is this is actually the point slope form of a line. Remember, our derivative finds a rate of change, or our slope. So this is our slope. A is my x coordinate. F of a is my y coordinate. So if you remember point slope, it's y minus y sub 1 equals m times the quantity x minus x sub 1. Well, this is x sub 1. All they did was add the y over. So this is a line, kind of like that tangent line. And we can use that tangent line to approximate on this graph. Now, obviously, so the point at which I am referring at is my center of the approximation. It's going to give me that exact value. As I go above and below that, or left and right of that line, I'm going to get farther. I possibly could get farther away from the approximation. Okay, so we're going to look at how to find that linearization. Okay, so the first one, here's my first example. I have f of x equals the square root of x plus 1, and I want to find the linearization at x equals 0. So the first thing I'm going to do is I'm going to write f of x in power form. So that becomes f of x equals x plus 1 to the half power. I'm going to take the derivative of that. So I'm going to bring my power down. 1/2, this inside stays the same, x plus 1, subtract 1 from the power, negative 1/2, times, and I didn't write it up here, the derivative of the inside is 1. Okay? Now, the linearization says L of x equals f of a plus f prime of a times x minus a. So I need to find f of a. So I'm going to go back up here to this equation, and I'm going to plug 0 in. So I plug 0 in, I get 1 plus 0 is to the half, so 1 plus 0 is 1, to the half power is 1. And I also need f prime of 0, okay? So I'm going to plug in 0 to my derivative. So 1/2 times the quantity of 1 plus 0 to the negative 1/2, so that gives me 1. 1 to the negative 1/2 is 1, so that gives me 1/2. Now I'm going to take these values and substitute them in for f of a and f prime of a. So I have 1 plus 1/2 times the quantity of x minus 0. That gives me half x. I'm just going to rearrange them to be more similar, to be y equals mx plus b. So Lx equals 1/2 x plus 1. Okay, so there's my linear approximation of this square root. And it works at 0, and it's close for values close to that. Okay, so now we're going to do one. We're going to work it out step by step. The nice thing is this is the same, so I already have my derivatives and stuff like that. So I know f prime of x is going to equal 1/2 1 plus x to the negative half. Well, I need to find f of 3 up here, so that gives me the square root of 1 plus 3, which is 2. Okay, that's good. I need the plugins. I need f prime at 3 also. So I get 1/2 1 plus 3 to the negative 1/2. So that's 1/2 times 1 over the square root of 4, which is also 2, so that's 1/4. Okay, now I'm going to go back up here and I'm going to plug everything into this. So L of x equals f of a, which is 2, plus my slope, which is 1/4, x minus 3. There's my linearization. I could multiply, I could distribute my 1/4, I could combine my 2 and 1/4 of negative 3. I'm just going to leave it like this. Okay, so that gives me my linearization at x equals 3. So you can have these, a lot of these for any given function. All right. So differentials. Differentials is let y equals f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals f prime dx. Okay. What we're going to do is we're going to kind of look at this. So if you remember, when we were talking about how we write the derivative, so when I have f prime of x, that's the same thing as y prime, which is the same thing as dy dx. And it's this piece right here that we want to focus on. Because what we're looking at in differentials is essentially kind of looking at how fast is the y changing given that x is changing this amount. Okay? So what we're going to do is we're looking at, so if I have an item here, and we'll just take this one, our example here is y equals x to the fifth plus 3x. Okay? And so what I'm going to do is I'm going to take the derivative of this. Well, this becomes dy dx, right? And this becomes 5x to the fourth plus 3. Well, what I'm really solving for in differentials is I'm solving for that dy. So I'm going to treat these as variables, and I'm going to multiply over by dx. And so now I have dy equals 5x to the fourth plus 3 quantity times dx. All right? And so now I can find my differential dy when x equals 1 and dx is going to be 0.02. So I'm going to take these values and plug them in. So dy equals 5, 1 to the fourth plus 3 times 0.02. Well, 1 to the fourth is 1 times 5 is 5 plus 3 is 8. So this gives me 8 times 0.02, which gives me 0.16. And so there's my dy on this. Okay? So when you're looking at these, just remember that you're going to take the derivative of both sides, okay? And that y we're going to leave as dy dx and then solve for dy dx. So if I have, let's do one more of these. So let's say I have y equals 3x squared plus 5x. Well, if I want my differential, what I'm going to do, take the derivative, okay? So dy over dx equals 6x plus 5. Bring your dx over. So dy equals 6x plus 5 times dx. There's my differential. Okay? Now what I can do is if I know x equals 2 and dx equals 0.01, I can plug this in. So my differential dy is going to be 6 times 2 plus 5 times 0.01, which is going to give us, this is 12, gives us 17 times 0.01, which is 0.17. There's my differential. Okay? You can use differentials to approximate and stuff. There is going to be, kind of like when you approximate, there's going to be some errors there. So that's linearization and differentials.